Let's go ahead and get started on Chapter 2. In Chapter 2, we're going to be solving equations and inequalities. So to start this chapter in 2.1, we're just going to look at some basic equations and determine whether they give us true statements or false statements. And then we're going to look at how to write solution sets. How do we communicate which numbers are solutions to the equation that we're given? Now remember to pause the video if you need to write something down, if you need to think about it. If you do that and you don't understand what's going on in the example, make sure that you write your questions down and ask those questions in class. Don't wait until your mastery check to start asking questions. Ask them right away. So right now, pause the video and write this definition of a number sentence. A number sentence is a statement of equality that involves only numbers. It's either always true or always false. So let's test these number sentences and see if they are true or false. Now, as you're evaluating each side of the equation, then you need to follow the order of operations, which says do any parentheses or grouping first, and then do exponents, those are powers, like x to the second power. Then do multiplication and division, and the last thing you do is addition and subtraction. So on our first example, we first want to multiply 2 times 2 and get 4, and then we want to add the 5. When we add those together, we get 9. Now look at the other side of the equation. We want to multiply 3 times 4, which is 12. And then we want to subtract 3. 12 minus 3 is 9. Since those evaluate to the same thing on both sides, we say that this equation is a true. Some of the math we can do in our head, but sometimes it's just easier to use a calculator. So in example 2, I'm going to put each side of this equation into my calculator. Be sure you know how to type this in as well. So the left side of that number statement said take the square root, so notice where those buttons are, of 25 plus 16, and all of that is under the square root symbol. I press enter and I get that answer, which is a decimal. I want to know, is that the same thing as taking the square root of 25 and then adding that to the separate square root of 16 answer, and clearly those are not the same number. So that tells us that this number inequality is false. Is another one that looks like it could be true, because 2 plus 3, if I add those exponents, I do get 5. But remember what exponents are. Exponents are repeated multiplication. So another way to think about 4 squared is 4 multiplied by itself. 4 to the third power is 4 times 4 times 4. And then on the other side, 4 to the fifth power is 4 used as a factor 5 times. Now the calculator can do these for me, so I'm going to type them in like this. 4 squared plus 4 raised to the third power. Make sure you follow those keystrokes. And then I want to know, is that equal to 4 to the fifth power? And you can see that 80 and 1024 are not the same number. So this is another number statement that looks like it might have been true, but it's actually false. Now let's look at how algebraic equations are different. Once again, pause the video if you need to write this definition down. An algebraic equation is a statement of equality, so there's an equal sign in it, that involves number expressions and or variable expressions. It may be true for some numbers and false for other numbers, or it can be always true or always false. Look at example 4. It's x divided by 3. When it's written as a fraction like that, you can read that as division. X divided by 3 plus 2 is equal to 6. Now, I don't know if that's a true statement or not because I have no idea what x is. So what we're going to do is we're going to test some values. We're going to test these same values in each of our equations to see if they give us a true statement. So the first thing we want to do is just substitute in -6 for our x. If I put -6 in place of the x, so I take the x out and put -6 in, then everything else in the equation stays the same. And I want to know if that's a true statement. Well, -6 divided by 3 is -2, and -2 plus 2 is 0. It's not 6. So that means that -6 is not a solution to the first equation. Let's test negative 3 in the same way. So I'm going to take out the x and put negative 3 in its place, divided by 3, and then plus 2. Negative 3 divided by 3 is negative 1, and negative 1 plus 2 is 1, which is not 6. So that one does not work either. Let's test the 0. If we let x be 0, then we have 0 divided by 3 plus 2. 0 divided by 3 is 0, and 0 plus 2 is not 6. So that one doesn't work either. Let's look at 3. If x is 3, 3 divided by 3 is 1, and 1 plus 2 is 3. So that one does not work in this equation. Let's test the 12. If I put 12 in place of the x and divide by 3, and then add 2, 12 divided by 3 is 4, and 4 plus 2 is 6. So finally we have a solution. Now there was no guarantee that we were going to have a solution from this list of numbers, and 12 was the only one that worked. So let's test these same values in our next equation to see if any of these values for x give us a true statement. I'm going to do the same thing I did before. I'm going to substitute negative 6 for the x. Now notice when I substitute, I have to take the x out when I put the negative 6 in. Now I want to simplify inside each group. Negative 6 plus 1 is negative 5. Negative 6 plus 2 is negative 4. And if I multiply negative 5 times negative 4, I get 20. And that's the other side of my equation. So that means that negative 6 works. That doesn't mean that it's the only number that works, so we need to go through and test our other values as well. Let's substitute negative 3 for x. So I get negative 3 plus 1 multiplied by negative 3 plus 2. Negative 3 plus 1 is negative 2. Negative 3 plus 2 is negative 1. But when I multiply those together, I'm not going to get 20. Test the other values and see which ones will work. When you substitute 0, you get 1 times 2, which is not 20. When you substitute 3, you get 3 plus 1 is 4, times 3 plus 2 is 5, and 4 times 5 is equal to 20, so that one works. Now if I substitute in 12, then I get 13 multiplied by 12 plus 2 is 14. And I don't know what that number is, but I know that it's not 20, so 12 does not work. Finally, let's test these same values in our last equation. So I have x to the second power, sometimes we read that as x squared, is equal to negative 4. So when I have a power, that means I'm using that base as a factor that many times. So if my x is negative 6, notice I want to put that in parentheses and square it. That's the same thing as negative 6 multiplied by itself. When I multiply a negative times negative, I get a positive 36, so that one doesn't work. Now hopefully you can see that if I put a negative number in and square it, that it's always going to end up being a positive number, not like a negative 4. When I substitute negative 3, that does not work. If I substitute 0, I have 0 times 0, which is not negative 4. If I substitute a positive 3, then I have 3 times 3, which is not negative 4. And 12 times 12 is 144. It's not negative 4. There's no way that you can square a number and get a negative on this side right here. So that's a clear indication that there are no solutions to this equation. And we'll see how to write that in our next set of examples. So in example 7, we have a very basic algebraic equation. X equals 5. It's already solved for us, but we want to look at how to write the solution verbally, graphically, and using set notation. Verbally just says that 5 is a solution. That's all you're saying when you say that x is equal to 5. So if I want to show that graphically, I could put it on the number line, and 5 is the only number that should have a dot on it because it's the only answer. For set notation, we use our squiggly brackets like this. It doesn't matter if they're not perfect, and we just list the solutions if that's possible. In example 8, instead of an equal sign, we have an equal sign with a line through it, which means does not equal. So if we think about this, if f plus 1 does not equal 4, then that means that f does not equal 3, because if f is 3, then 3 plus 1 does equal 4. So verbally, we would say our solutions are f cannot equal 3. Graphically, the way we show that is that on the number line, any of the numbers are fine except 3. So what we do is we put an open circle to say we're not including the 3, and then we shade all the other numbers that are possible. And any number except 3 will work. For set notation, we use our squiggly lines, and there's no way to write this by listing every value because we can't list all those numbers. So we say x is not equal to 3. Let's take a second to look at the different ways that we could have set notation. Now, in the last problem, I wrote the simple case, just the brackets and x is not equal to 3. Another way that you can write that is to say, with the squiggly brackets, x is an element of the real numbers. That's what this double back R means. And then this vertical line means such that, and then x is not equal to 3. So sometimes you'll see it written that way. Another advantage to this is that you could say things like x is an element of the integers, and integers means no fractions, but positive and negative numbers, such that, and then you could say x is not equal to 5, or whatever your solution set is. So you'll see some variation on that set notation, but if you stop and just think about it a little bit, it'll usually make sense. If it doesn't, then ask a question. In example 9, we want to know what values of y satisfy y squared equals 9. So if I have y squared, that means I'm multiplying y times itself, and I want to get 9. And there are two things that'll work. I can multiply 3 times 3, and that would give me 9, or I could multiply negative 3 times negative 3, and that would also give me 9. Those are the only two numbers that when I multiply them like that, they're going to give me 9. So verbally, I would say x equals 3 and x equals negative 3 are solutions. If I want to show that graphically, I'm going to show it on the number line. And I'm just going to put negative 3 and 3. Make sure you put them in order with the small number on the left and the larger number on the right. And I just want to put solid circles right there on negative 3 and 3. For set notation, and let's go with the fancy way, we're going to say x is an element of all real numbers such that x equals negative 3, comma x equals 3. And if I didn't want to put the x equals, that's okay. I could just put negative 3 and 3. Notice on example 10, instead of having an equal sign, we have an inequality. We have less than or equal. So if we simplify that, q minus 4 is less than or equal to 10, that means that q is less than or equal to 14, because 14 minus 4 would equal 10, and that would be our boundary. So verbally, if I was going to say that, I would say q is less than or equal to 14. If I want to show that on a graph, then I'm going to start with my boundary number of 14, and then I want to shade in the direction of the inequality. So I want to include the 14 because of the equal sign, and I want to shade to the left. So this arrow at the end of the number line matches my inequality symbol as long as my variable, my letter, is on the left side. Now for set notation, I can say x is an element of the real numbers such that x is less than or equal to 14, or if you want to put the verbal statement inside the set, then you can do that. If you take a look at this last equation, I hope you recognize this distributive property right here, that 2 times x plus 3 is 2x plus 6 by distributive property. Since that property is always true, then all real numbers are a solution. Any number will work. Graphically, we want to shade the entire number line, And for set notation, we can write this double back R, which represents all real numbers.